We're still continuing the problem on preparation of buffers. This is a second very useful method of preparing buffers, and it depends on having a weak acid and adding a certain amount of OH minus, a strong base, and that OH minus is in limiting amount, not so much is added. And we will see what will happen to the solution upon adding OH minus. Okay, we can also sometimes decide how much OH minus should I add in order to prepare a buffer solution of a certain pH. And those are fairly nice questions where they don't tell you how much OH minus there is, and you have to find out how much you should add. All right, so let's start with the easier and then go harder, okay? So number 48.1 or 48 part 1, if we have 0.5 moles of NaOH are added without change in volume to a 1 liter solution of a weak acid of concentration 0.1 with a pKa of 5.2. So they didn't tell me which weak acid it is, doesn't really matter. What is the final pH of the solution? So here at the moment, we don't really know what's going to happen to the solution or until we do a stoichiometric calculation. So of course, this weak acid will react with my strong OH minus upon mixing. And of course, yeah, you will produce A minus and water, just proton transfer. The amount of moles, we're going to use a moles chart, sometimes millimoles chart, depending on the question given. So here we have a 1 liter solution of acid, of HA acid, and therefore times 0.1 molar, we get 0.1 mole of the acid. And the amount of OH minus was given to us in moles, and they said there was no change in volume, so the overall volume is pretty much the same for the solution. It's still 1 liter. Once the reaction takes place, what will happen? Of course, we can look at the amount of OH and we say, oh, okay, that's less than HA. And always, guys, if we have on the reactant side OH minus or H3O plus, it's a one-way reaction. The reaction will go all the way. At the moment, we have no A minus in solution. Okay, at the moment, before initial, we have no A minus. Once the reaction proceeds, of course, my OH is my limiting reagent. It tends to 0. There's nothing left of it. And all of this amount actually reacts. And so you get minus 0.1 minus the amount reacted, which is 0.05. I'm left with only 0.05 mole of HA. Of course, I end up producing a plus X amount, which happens to be 0.05 on the product side, and that means A minus is now this 0.05. What is now my solution? What did I end up with? I ended up getting a mixture, finally, with HA and A minus. And guess what? They're in equal amounts. What is this mixture? It's a buffer, of course, or, you know, hopefully a buffer, like at least it's a common ion effect, and which we still use the Henderson for, where we use the 0.05 moles of the base and 0.05 moles of the acid. And of course, their volume is 1 liter, and you don't really need the volume because it cancels out. And because their concentration is the same, actually that's it. The pH of such a solution is simply equal to the pKa of the couple, HA minus. Clear? Very simple. And the next part is as well Okay, in this question, part 2 of number 48, it asks for, if I have the same solution, 100 milliliters was added to that solution, what will the final pH of that solution be? Remember, guys, the final pH, will it decrease by 2 pH points? Will it remain the same? It's a he. It increases by 1.3 pH units, and it has increased by 2 pH units. I like the he here for pH, okay. So he, the pH, what will happen to the pH? Of course, he, the pH, will remain the same. What? Dilution does not affect the pH of any type of buffer. So again, just a proof to you. So if I have, again, the moles of the acid divided by the base was 0.05. So if my volume was 1.1, because 1.1 liters or 1 liter, there isn't any difference because they cancel each other out. Okay, next question. This is a successive type reaction, and eventually we're going to end up producing a buffer. But first, we have a mixture of more than one acid-base couple. So in a 250 milliliter beaker, we introduce 40 milliliters of acetic acid at 20 millimole per liter. We then introduce 20 milliliters of HCl at 10 millimole per liter. It's a bit odd that they use 10 millimole per liter. I've never seen that before. But anyhow, they in one of the years, I didn't even notice this 10 millimole. 30 milliliters of NaOH at 20 millimole per liter, and 110 milliliters of water. So they mixed all that together. Calculate the pH of this whole solution glob. So first of all, you of course all know, if I have a mixtures of weak and strong acids or whatever, the strongest acid reacts first with the strongest base. And no, I really don't need here a pKa diagram in order to know who's going to react with who. Of course, the HCl will react with the NaOH first. Okay. And this reaction goes and finishes up before the other one even starts. So we have, what's the number of moles of HCl? We take the 20 millimoles, so I'm going to convert this to moles, so times 10 to the minus 3 mole per liter, times 10 milliliters. So that's the amount of millimoles of HCl that I have in solution, which is of course H3O plus. The number of moles or millimoles of NaOH, that's 30 times 10 to the minus 3 because they gave me the concentration in millimole, times 30 milliliters is again 0.6 millimole. So if you multiply milliliters by the mole per liter, you get it in millimoles. Okay. So here's my reaction. HCl plus NaOH gives me the salt NaCl plus water, but of course you don't need that. You just need to know that the HCl is H3O plus, NaOH is OH minus, and we actually produce 2 water molecules. That's my net equation. Of course, you all know that this equation is very complete, 1 divided by Kw, because the opposite of it is Kw, which means that this K for this reaction is 10 to the 14th. So starting, we have 0.2 millimole of H plus and 0.6 millimole of OH minus. Again, this will be very useful for you as examples for later on for our titration. This is just a titration of a strong acid with a strong base. You multiply the concentration by the volume. Concentration by the volume. I like to keep the volumes in milliliters and keep the concentrations in moles per liter. And then we get millimoles. And just because, you know, I don't have to put times 10 to the minus 3 each time. But of course, it's up to you. You can also use mole per liter times liters, but then you have to multiply by 10 to the minus 3. Okay, who's the limiting reactant here? Who's less? Of course, the H3O plus is less. So that's going to tend to 0. Nothing's going to be left of it as the reaction proceeds. But I am going to get some leftover OH minus. How much left over? 0.6 minus 0.2, which is 0.4. Of course, we produce water, but useless. It's already in great excess. What do I have left in the solution? Oh, I'm done. I have 0.4 millimoles of OH minus. But that OH minus will go further and now react with the next acid in solution if there is any. Okay, and yes, there is one. There's acetic acid. So the leftover NaOH will go ahead and react with my acetic acid. It was 20 millimoles, so 20 times 10 to the minus 3 times 40 milliliters, I have 0.8 millimoles in the solution of acetic acid. And we do a mole chart or a stoichiometric chart as if we're doing a titration. Again, these types of charts are very useful for titration. I really, if it was up to me, I would keep all these types of reactions after titration because you would have done a lot of that. But it's good now. Here, this will give you head start towards titration anyway. So we have acetic acid initially in solution of 0.8 millimoles. How much OH? That's the amount left over after it had reacted with HCl, is 0.4 millimoles. Of course, we have no acetate in my solution initially. So who's the limiting reagent? Yes, it's the less amount, which is the OH minus. So all the OH minus will actually run out in solution, and the acetate will be remained. The amount remained will be 0.8 minus the 0.4, which happens to be 0.4 millimole. How about the acetic acid? How much do I have in solution? Yes, I have the same amount as my limiting reactant, so that's 0.4. What do I have in this? What is this left over? Do I have to do more reactions? Are there further reactions that can take place? No, I have no more H plus, I have no more H minus. And I simply have acid and its conjugate base, of course, which they will react with water, if you remember. The acid and the base will react with water to give me whatever pH. And of course, when we have acid and base, I don't have to do that reaction in water. All I have to do is use Henderson. Great. Okay, so this is a mixture of a weak acid and its conjugate base. The pH of this buffer-like common ion solution or a common ion solution is to use Henderson. So use Henderson, you have the pKa plus the log of the base divided by the acids. And of course, you can just keep these in millimoles divided by each other, because if you convert them to moles per liter or concentration, that amount will simply cancel out. Okay, so keep them in millimoles and you get that the pH of the solution finally is 4.80. Okay. We're now still at the process of preparing a buffer by adding some acid to an OH minus, let's say. And here actually they're going to prepare a buffer solution eventually from an amphoteric salt, NaH sulfate. Bear with me and you will see. Now in the question they say consider a 1 liter buffer solution of sodium hydrogen sulfate. That's very wrong. At the moment, the sodium hydrogen sulfate is definitely not a buffer. This is a salt solution. What type of salt is this? Yes, you're right. To remove the sodium, it becomes HSO3 minus anion, which is an amphoteric salt. Okay, calculate the pH of the solution. So do I use the Henderson? Well, they said buffer. Do I use Henderson? No, guys. This is not actually a buffer. This is sodium hydrogen sulfate, okay? This is not a buffer. So we're going to just go ahead and do part A for now. What is the solution? This is, of course, a salt, and it's an amphoteric salt. Hydrogen sulfate can act as both an acid or a base. What's the pH of an ampholyte or an amphoteric substance? Yes, the pH of an amphoteric substance is half pKa1 plus pKa2, because this is a diacid. Okay, so that has a pKa1 plus pKa2. And of course, they do give you the two pKa values for the couples, and you simply substitute it in and you get 4.6. Okay. So that was part A. That was easy, though they made it a bit more complicated when they added the word buffer. However, in the next part B, that may well be a buffer type solution. Let's see part B for the moment. Okay, so we were talking about part B. So we have the sodium hydrogen sulfite, not sulfate, sulfite, of concentration 0.1 molar. We're going to add to that solution, which is an ampholytic solution, without any variation of volume, so we still have a volume of 1 liter, 0.05 mole of NaOH. To obtain a new solution, they called it S, and they want the pH of this solution. Okay, so we have, of course, the hydrogen sulfite, and of course it will react with OH minus. Can it react? Yes, it has a proton. Okay, so this OH picks up the proton, it becomes SO3 minus and water. What about this reaction? Regardless whether it is complete, it is not complete, as long as I have OH minus as a reactant, guys, you will put a one-way arrow. Nonetheless, this is a complete reaction. This is the K for this reaction. Look at this couple. This is HSO3 minus with SO2 minus. So this is a Ka2. The acid on the reactant side divided by the acid on the product side, which is the water, divided by Kw. So the K reaction turns out to be indeed a complete reaction. But regardless, again, you don't have to do this. The minute you see OH, you go a complete reaction. Put the number of moles. We always do a complete reaction and we use a mole chart. Okay, put in the mole chart. We have 0.1 moles of the of this acid, HSO3 minus. It's acting as an acid here, and 0.05 mole of OH minus. I have at the moment no SO3 minus. Look at this OH. Yes, it's limiting. It has a small amount or smaller amount than the acid or than the ampholyte. Therefore, it's going to tend to 0, and I'm going to produce 0.05 mole of the hydrogen sulfite and 0.05 mole of the SO3 minus. Of course, guys, you really, at the next step, you really don't have to do a calculation. You can just simply say what? You have equal amounts of the acid and its conjugate base. This is a buffer. Of course, you can use Henderson, but right away, guys, these are the same amounts. The pH equals the pKa. Which pKa, though? Watch out, which pKa? It's the second pKa, because look at these two couples. This is the second dissociation of the H2 sulfate. Okay, so this is pKa2, because this is the second couple of that acid dissociation. Okay, great. Part C of that same question is now to maintain pH, actually, of this new buffer that we have formed. So at the moment, yes, we have. Okay, so what are Okay, sorry, I did something here. It was still recording. Okay, so what were we doing here? We had the buffer that we just formed in the previous part. And so they considered that solution S, which was the buffer already formed. Without change in volume, we're going to add 0.05 mole of HCl, calculate the new, the pH of a solution, new solution, actually, it should be S prime here, and discuss, okay? So solution S, we had 0.05 mole of the sulfite, the SO3 2-, and the 0.05 mole of the hydrogen sulfide as a buffer system. So when we add HCl, what happens? What will it do? Come on, guys, what will it do? Yes, of course, the HCl, of course, you all know it's H3O+, and that H3O+ will be neutralized by the base of my buffer, of course, by the SO3 2-. We will react H3O+, and we get HSO3- and water. And of course, as long as I have H3O+, the reaction is complete, irrespective of these values, okay? But up here, of course, Ka2, the K reaction does turn out to be complete. Let's put the number of moles with our mole chart. 0 initial moles is 0.05. Of course, I now already have some hydrogen sulfide, 0.05. And now I'm adding extra to this buffer system an OH3-. Okay? Don't forget here that we already have some HSO3-. Okay? Now, if we didn't, that would be 0. We would probably still get a buffer at the end, but that's not the question, okay? Here, of course, you can see that the H3O- is limiting amount, so that's going to tend to 0, and I'm going to produce, remove some SO3-, 2-, 0.05 minus 0.01, which is I'm left with 0.04, and product side that's going to add some more. So how much is going to be added? 0.05 plus the 0.01, which is 0.06. What am I left with? Yes, a modified buffer or an adjusted buffer with slightly modified moles. What do you use? You use Henderson, check it out, that same equation, still pKa2, I still have those same couple, but look, the ratio now for the acid and the base is slightly different. It was 0.5, 0.5, now it's 0.04 for the base and 0.06 for my acid, and divided by total volume, of course, which is, you know, you don't even have to include anymore. Look at my pH, it's 7.02. Slightly different than the 7.2, but not that much. And so as well, amphoteric buffers, amphoteric type buffers like this one, can also, or this is also a buffering system that can maintain pH. Okay, and that's showing that it's maintaining pH. Great. Number 44 is actually a theory type question. Let's go through one step at a time. Which of the following statements are correct concerning a buffer solution in water? The pH of a buffer solution is sensitive to moderate dilution. The buffering capacity of a buffer increases upon decreasing its concentration. Upon mixing n moles of a weak acid and n moles of sodium hydroxide, we obtain a buffer. Mixing n moles of weak acid and n divided by 2 moles of sodium hydroxide, we obtain a buffer. Mixing of HA with 2 moles of sodium hydroxide, we obtain a buffer. Okay, we're going to go through each of these one at a time. One at a time, I said. Okay, let's... Okay, so let's look at A, okay, in details. They're saying that the pH of the buffer is very sensitive to moderate dilution. pH of a buffer is sensitive to dilution. Of course not. pH of a buffer is not at all affected by dilution, right? We saw that 2 times in 2 examples. The buffer capacity of a buffer, remember, what is buffer capacity? It's the ability to pick up the extra acid or maintain buffer or extra base. Its ability to pick them up without any change in pH. And we said that the buffer capacity is best when the HA and A- are close to each other, when the pH equals or is very close to the pKa of the buffer that I want to make, or that the pKa of the buffer system is close to the pH that I want to buffer. And last but not least is that the concentration of the acid and the base are actually best when they're larger. So when your initial concentration is large. When the initial concentration is actually small, you could only pick up a certain amount of acid or base in the medium. And so the buffering capacity of a buffer solution increases upon decreasing its concentration is incorrect, actually. It's best when the concentrations are large, okay? When the concentration of the buffer is, of each of the acid and the conjugate base are large. We call it largish. Usually it should be, you know, greater than 0.1 mole per liter. Okay, upon mixing, part C, upon mixing n moles of a weak acid, so we have n moles, with n moles of sodium hydroxide, what will happen, guys, if I have the same amount of acid and OH minus? We saw similar, well, we didn't here, but if I have equal amounts of moles, n moles of acid and n moles of HA, all of the HA will become A minus, right? All of the HA will become A minus, and therefore here we have equal amounts. That's not good, and that's the equivalence point, if you will, when we get to titrations, and then we end up only getting A minus in my solution, because all of the acid and the base will be neutralized together. So in my solution net, I will only get n moles of A minus, and I have no HA left over. Okay, let's look at part D. For part D, if I have n moles of a weak acid with half the amount n divided by 2 moles of sodium hydroxide. Well, now the sodium hydroxide is the limiting reactant, so there's less of it. So indeed, in my solution left over, I'm going to have some leftover HA, which is n divided by 2, half of it. And I'm going to produce some n divided by 2 A minus and as well water. So indeed, I do end up forming a buffer with a good buffer with equal amounts of acid and its conjugate base. So D is actually a good choice. Let's check out E. Oops. Okay, upon mixing n moles of an acid with 2 n moles of a hydroxide, well, automatically they have more hydroxide here than I have acid. So all of the acid will be removed in my system, and I will end up having a system with leftover OH minus n moles and some produced Na minus, and actually this system will end up become basic. And you're going to see a lot more of these types when we get to titrations, and titration is going to be so easy for you after all this. So of course E is incorrect. So my only correct answer is D. Okay. And that's it, okay? And I'm gonna, like I said, do this number 40 at the end.